From tropical rainforests to deserts, the Earth's surface is shaped by the action of running water. As raindrops fall or snow begins to melt, some of the water sinks into the ground and through the process of infiltration eventually adds to the groundwater supply. Some rain or snow falls directly onto water surfaces as channel precipitation. The rest of the water flows from higher to lower ground under the pull of gravity. Runoff begins as overland flow after the ground has become saturated. This runoff may spread into a sheet of water for short distances, then divide into rills and rivulets in its course toward lower ground. In areas with sparse vegetation or easily eroded soil, the rills and rivulets combine into larger channels called gullies. Eventually, the overland flow either sinks into the ground or finds its way into a stream. A stream is a flow of water normally confined to a well-defined channel. Each stream has a source, or point of origin, and a mouth, or endpoint, where it flows into another stream, into a basin of interior drainage, or into the sea. A stream's size at any given point along its course can be measured in terms of discharge. Discharge is the volume of water flowing past a particular point in a given period of time. It is expressed in cubic meters or cubic feet per second. The amount of discharge often varies greatly from season to season and from year to year, depending on amounts of precipitation. Most streams in humid regions are perennial. This means that water flows in their channels throughout the year. Most streams in desert regions flow only during and shortly after rains. These are called ephemeral streams, from a Greek word for short-lived. A few large rivers, such as the Colorado, the Indus, and the Nile, have enough water in their channels when they reach dry regions that they maintain a perennial flow across the deserts. These are called exotic streams because they originate in well-watered areas far from the deserts through which they flow. Streams vary from tiny trickles that drain very small areas to mighty rivers that drain enormous regions. Various terms are used locally to describe streams of different sizes and flow patterns. A river, for example, is thought of as a large stream, generally with several smaller tributary streams feeding it. Small streams may be called brooks or creeks, depending on local usage. The word bayou is used in Louisiana for sluggish streams, some of which flow along old channels of the Mississippi River. In some regions, a fast-flowing mountain stream is called a torrent. None of these terms are precise, however, so geoscientists distinguish between orders of streams. A first-order stream has no tributaries. A second-order stream has only first-order streams as tributaries. A third-order stream is formed when two second-order streams join waters, and so on. There are far more low-order streams than high-order streams. In the United States, for example, there are approximately 1.5 million first-order streams, about 4,200 fifth-order streams, but only one 10th-order stream, the Mississippi River. In addition to being more numerous, low-order streams are generally shorter and have steeper gradients than high-order streams. Low-order streams also drain smaller areas. As defined by geoscientists, each stream has its own drainage basin, or area from which it transports water. This basin is bounded by a drainage divide of higher ground that separates one stream valley from another. The drainage basin, or watershed, of a first-order stream is composed only of the valley bottom and sides that drain into that particular stream. The drainage basin of a major river, however, includes the drainage basins of all of its tributaries. Consequently, the higher the order of the stream, the larger the area that is drained by the stream and its tributaries. A typical first-order stream in North America drains about 2.5 square kilometers, whereas the Mississippi and its tributaries drain 320 million square kilometers. A stream system is composed of all the streams that join in a drainage network to carry water from a drainage basin or watershed. A majority of stream systems eventually pour their waters into the oceans. A few, however, terminate in basins of interior drainage. These may contain landlocked lakes such as Utah's Great Salt Lake, or be marked by extensive salt flats, where waters of ephemeral lakes have evaporated in the desert sun. In all cases, however, the water flowing through a stream system seeks the path of least resistance and changes the landscape as it does so. Processes related to the channeled flow of water are called fluvial processes, after the Latin word fluvius, which means river. Major fluvial processes involve the work of running water in modifying landscapes through erosion, transportation, and deposition of earth materials. Stream systems are highly dynamic. As they cut down their beds and wear away the materials along their banks, they act as powerful agents of erosion. However, no stream can erode its bed any lower than the base level to which it flows. Streams flowing into the ocean have a base level at sea level. For streams joining other streams as tributaries, the base level is the water level of the main stream at the point of confluence. The bottom of a basin is the base level for streams that drain into interior sumps, some of which, such as Death Valley, are below sea level. For a stream flowing into a lake, the lake surface is the base level. A temporary base level may form above erosion-resistant rocks, as seen at Popo Falls on the Okavango River in southern Africa. Watch a small stream flowing across a sandy beach to reach the sea. As the tide goes out, thus lowering the base level toward which the stream is flowing, its gradient and velocity increase as it cuts deeper into the sand. The stream's load of sand, meaning the amount of material it can move, increases as it erodes its bed and banks. A few hours later, as the tide comes in, the base level is raised and the stream drops some of its load. Base levels may change through time, thus affecting the stream's work as an agent of erosion and deposition. Over long periods of time, world sea levels change, creating major changes in stream system dynamics, especially in their lower reaches. During any given time period, rates of erosion vary from one stream to another, and also along the course of any single stream, depending on such factors as the stream's volume, velocity, the kind of rock over which it flows, and the cutting tools in its load. The bed load, which may remain in place when the stream is low, is composed of the material pushed downstream by the force of running water. Large pieces of rock move by sliding and rolling down the stream bed. Lighter rock materials may move down a stream bed by saltation, meaning that they jump and bounce downhill as they are pushed by the moving water. The sand, gravel, larger stones, and other materials pushed along by the water, serve as cutting tools. They grind away or abrade materials along the stream's bed and sides. As rocks tumble downstream, their sharper edges are worn off. This produces rounded stones of all sizes. Gradually, rocks are reduced in size through the process of abrasion until they are turned into sand or even smaller fragments. Streams carry very small particles or sediments such as silts and clays in suspension. A murky or muddy color generally indicates a large sediment load in suspension. Dissolved minerals are carried downstream in solution. These materials are added to the flow as running water chemically dissolves soluble minerals in rocks such as sandstone or limestone. The amount of load a stream can carry depends on its volume and its velocity. The larger a stream and the faster it flows, the more load it can carry. A large deep river flows with high velocity. It can carry large loads in suspension even when the gradient of its bed is low. The gradient, or slope of a stream bed, is its vertical drop over a given unit of horizontal distance. Gradient strongly affects velocity. With a given amount of discharge, the steeper the gradient, the greater the velocity. Turbulent flow is irregular, with currents moving in many directions. Turbulence is increased by steep gradients and high velocity, as well as by roughness in the stream bed. As rafters know, streams may flow gently along for miles, then suddenly froth into rapids at places where the stream bed gradient steepens, usually as the result of flow over erosion-resistant rock layers. A waterfall occurs where the riverbed makes a distinct vertical drop. Steep drops in elevation along a stream course, with the steeper section downstream, are called nick points. These drops are sometimes due to faulting or the uplifting of the regions where the stream originates. Nick points also indicate areas where the river is cutting through layers of resistant rock. Rivers flowing over resistant rock, as at Niagara Falls, erode headward or upstream as bed erosion wears back the cliffs. Headward erosion is also common at the head of stream valleys and may, through time, result in a lengthening of a valley as gullies cut into the higher ground between watersheds. As a stream begins downcutting its bed, it typically has many rapids and waterfalls along its course. Most of the stream's energy is used to smooth out irregularities in its gradient. A swift-flowing stream with many cutting tools may carve its bed down rapidly, thus forming a steep-sided gorge or canyon. Such stream-cut valleys typically have V-shaped profiles, as seen here in the Grand Canyon of the Yellowstone River. Falls have developed where the Yellowstone River flows over an intrusion of igneous rock that is much more resistant to erosion than the loosely consolidated volcanic debris and lakebed sediments up and downstream. Although the valley remains narrow at the bottom as the river continues cutting down, it widens at the top. Canyons with nearly vertical walls are sometimes found in plateau regions. This happens when a stream cuts rapidly through rocks to great depths, as seen here along the Little Colorado River. Due to the composition of the rocks, along with the dry climate, the widening of the valley through weathering and mass wasting takes place very slowly. At Arizona's famous Grand Canyon, the walls form a series of cliffs and slopes. This formation developed because of the differential resistance to erosion of various rock layers as the Colorado River cut down more than a mile into the rocks of the Colorado Plateau. A fast-moving stream flowing down a steep gradient spends most of its energy deepening its bed. As a river carves out its downward course toward base level, it develops a relatively smooth concave-shaped profile and begins to maintain a balance between its transportation capacity and its sediment load. As gradient declines, the stream develops a curving course, eroding the sides of its channel and widening its valley in a process called lateral erosion or side cutting. As lateral erosion continues, the river's curves or meanders become more pronounced and the valley floor widens. At each bend, the current swings against the bank at the outside of the curve, eroding it rapidly. On the inside of each curve, velocity is low and materials are deposited to form sand or gravel bars called point bars. As the process continues, the meander loops become more extreme and eventually the stream breaks through the narrow neck of a meander, thus forming a cutoff. Most of the flow goes through the shorter, steeper cutoff route. As sediments are deposited along the old entrances to the meander, the cutoff loop becomes completely detached from the stream. The water-filled remnant of a former channel is called an oxbow lake. Gradually, the stream broadens its valley as it meanders back and forth across the nearly level valley floor that it has created. This valley floor is known as the floodplain. The stream bed or channel is that area generally covered by running water. In navigation, the term channel is used in a more restricted sense to refer to the deepest part of a riverbed. The stream banks are the edges of the stream bed. When a river contains so much water that it overflows its banks, it is in flood stage. The flattish land on either side of the river, which receives this overflow, is part of the floodplain. Some rivers in low-lying humid areas frequently overflow their banks, inundating the lower parts of their floodplains. The floodplain is filled with deposits of alluvium, left in old river channels and deposited by floods. Floodplains are usually important for agriculture because of the richness of alluvial soils. Even in nearly level terrain, the edge of the floodplain is usually marked by a relatively steep slope or a line of bluffs. Floodplains along the lower reaches of large rivers, such as the Mississippi, are characterized by numerous bends and oxbow lakes. In their lower courses, many streams are more important as agents of deposition than as agents of erosion. If a stream is carrying its maximum load, deposition of materials will take place whenever and or wherever a reduction in the velocity or volume occurs. A sluggishly flowing stream, which receives more load from its tributaries than it can carry, tends to drop much of the load along its bed. Such streams are said to be overloaded. Streams such as the Platte River that wind in and out between many sandbars and islands are called braided streams. Braiding also occurs when a stream flows through an area with much coarse, loose material. As streams periodically overflow their banks and spill out over floodplains, they deposit the load carried in suspension. Heavy deposits of sediment are found along the banks because of the sharp reduction in velocity at the channel's edge during flooding. This creates natural levees that rise higher than the adjacent floodplain. Along great rivers, such as the Mississippi and the Rhine, natural levees have been augmented by much higher man-made levees. Although levees reduce the frequency with which water spills out over the floodplain, they also force the river to drop most of its flood load in its channel. This builds up the riverbed until the stream may actually flow higher than the surrounding plain. When a river enters a relatively quiet body of water, such as a lake or the sea, it completely loses velocity and deposits all of its sediments near its mouth. In this satellite view of the mouth of the Mississippi, one can see the sediment plume extending far out into the Gulf of Mexico. As the river drops its load, the sediments may form a fan-shaped deposit called a delta. As shown in this satellite view of the snow-covered Yukon Delta, rivers divide into numerous distributaries as they flow across their deltas. This happens because sediments block the channel and the river seeks other paths to the sea. Unlike tributaries, distributaries flow away from the mainstream. Not all rivers form deltas where they meet the sea. Materials dropped by small streams flowing into the open ocean are soon swept away by waves and currents. In other cases, rivers reach the sea through estuaries or drowned mouths that are formed when sea levels rise or when coastal areas are lowered. In these estuaries, salt water moves far upstream during high tides. When the tide goes out, large expanses of mud flats typically surround the fresh water flowing out to sea through the river channel. Ultimately, some of the water flowing out to sea is returned to the atmosphere through evaporation from the ocean surface. Eventually, this moisture vapor condenses. As clouds form, the water reaches the land again in the form of precipitation. Thus, a watershed is an excellent example of an open system with materials and energy moving through it. Water enters the system through precipitation and leaves either through evaporation or when the stream system that drains the basin flows into the ocean. The movement of water in the stream transforms its potential energy into kinetic energy that enables the water to carry its load of sediment